All right, so get this. We're diving into a paper all about making AI language models, more efficient.
Yeah, and this one is really making waves, like big waves in the AI world.
No kidding. The title is a mouthful, though. Native Sparse Attention.
Colon.
Oh, right, colon. Hardware aligned and natively trainable sparse attention.
Catchy, right.
Well, the content definitely is. It just dropped online February 14th, so super fresh.
And it's tackling like a huge problem holding back, advanced AI.
You're talking about making language models that can handle really long contexts, right?
Exactly. Like imagine processing a whole novel and then answering questions about it, that kind of thing.
Yeah, the implications are wild, like really in-depth reasoning, complex code generation, those multi-turn conversations that actually make sense.
It all requires the AI to remember and process tons of information. And that's where it gets tricky.
Because with the standard way of doing it, attention mechanisms, they become a real bottleneck when the text gets longer.
They try to analyze everything equally, which, let's be honest, isn't how we actually read or think.
Totally. And it's not efficient at all, especially for real-world stuff.
I mean, the paper even says that with 64,000 words, standard attention can eat up like 70 to 80% of the processing time.
That's insane. It's like using a fire hose to water a single plant.
A very thirsty plant, maybe. But yeah, it's overkill, and that's where this idea of sparse attention comes in.
So instead of trying to analyze every single word, it focuses on the most important parts of the text, right?
Right, like imagine a detective, right? They don't obsess over every detail at the crime scene. They look for the key clues.
Okay, that makes sense. So are there already ways to do this sparse attention thing?
Oh yeah, definitely. There are a bunch of different methods out there. Some trying to shrink that key value cache. It's basically the AI's memory bank.
And others try to reduce the number of calculations the AI has to make, right?
Exactly. But they all hit limitations, especially when it comes to actually training these huge AI models.
Ah, so it's not just about using the information efficiently, it's about learning it efficiently, too.
Precisely. And this paper points out two major hurdles that these existing methods can't quite overcome. The first one is hardware-aligned inference speedup.
Meaning?
Well, an algorithm can look amazing on paper, theoretically perfect, but if it doesn't work well with the way computer hardware is actually designed, it'll be slow in practice.
So it's like having a Ferrari engine, but putting it in a tiny go-kart. Not going to get you very far.
Huh. Yeah, something like that. And the second hurdle is training-aware algorithm design.
Go on.
Well, most methods focus on making the AI use information efficiently, but not necessarily learn it efficiently.
Okay, I see. It's like teaching someone to speed read without making sure they actually understand and remember what they're reading.
Exactly. And this is where native sparse attention, or NSA, steps in. It aims to tackle both of these limitations head on.
And that's what this paper's all about, right?
Yep. The researchers claim it's a breakthrough in both speed and accuracy. They've taken a totally different approach, basically baking sparsity into the model's architecture from the ground up.
Sounds like a pretty radical idea.
It is, and it seems to be working.
Okay, I'm hooked. So tell me, how does NSA actually work? What's the secret sauce?
Well, it's based on three main components: token compression, token selection, and a sliding window mechanism. Each one plays a key role in getting that sweet spot of efficiency and accuracy.
Okay, let's unpack that a little bit. What exactly is token compression?
Think of it like summarizing chunks of text, getting rid of unnecessary fluff. You're basically extracting the core meaning from a long passage.
So it's not just about throwing words away, it's about distilling the essence, right?
Yeah, exactly. But how does the AI know what to compress and what to keep in full detail? That's the next part.
Token selection.
Right. And instead of trying to pick out individual words, which takes forever computationally, NSA uses a blockwise approach. It selects whole chunks of text based on their relevance to the task at hand.
Oh, I get it. It's like grabbing a handful of puzzle pieces that fit together instead of picking them out one by one.
Exactly. Much more efficient. And the researchers actually found that words close to each other often have similar levels of importance.
So it's not just chopping things up randomly. They're actually capturing the natural flow of language.
Precisely. It's like they're working with the grain, like you said before, instead of against it.
That's smart. All right, so we've got these compressed chunks of information, and we're selecting the most relevant blocks. What about that sliding window you mentioned? What's that all about?
That's like the AI's short-term memory. It focuses on the most recent part of the text.
So it's like remembering the last few lines of a conversation to make sure you're following along. Our brains do that all the time, right?
Exactly. We naturally focus on the most recent information to make sense of things.
Makes sense. So by combining compression, selection, and this sliding window, NSA creates a sparse attention mechanism that's super efficient and surprisingly really effective too.
That's the claim, at least. But the proof is in the pudding, right?
Exactly. So how well does it actually perform? Does it live up to the hype?
Well, the researchers really put NNA through the ringer. They tested it against those full attention models and even other sparse attention methods.
And how'd it do?
It held its own. Like, it performed as well or even better than the others on standard language tasks, even with limited context.
So it can handle the basics. What about those really long texts, the 64,000 word monsters we talked about?
That's where it really shines, honestly. Like, remember how standard attention models just choke on those?
Yeah, it's like asking them to climb Mount Everest. Too much.
Right, but NSA, no problem. On those complex tasks like question answering or code understanding with super long contexts, it just blew the competition away, even the full attention baseline.
Okay, hold on. That's a bold statement. Give me an example, like something concrete that shows how much better it is.
Okay, picture this. There's this test called Needle in a Haystack. Basically, the AI has to find a specific piece of info buried in a huge chunk of text. Like, imagine trying to find a single typo in, like, a whole encyclopedia.
Oof, yeah, good luck with that.
Well, with a 64,000 word context, NSA found the needle every single time. Perfect accuracy.
No way. So not only is it faster, it's actually more accurate when dealing with massive amounts of info.
Exactly. And they didn't stop there. They wanted to see if NSA could handle even more complex stuff, like tasks that require real deep thinking.
What do you mean?
Well, they tried using it to train a model to solve tough math problems, the kind that need logic and step-by-step reasoning, not just simple calculations.
And did it work? Could it solve those problems?
It did. It actually figured out those math problems, which means this approach isn't just about surface understanding. It can actually do some deep conceptual thinking.
That's a huge leap forward. So we know it works, but how much faster are we talking here? Like, what kind of efficiency gains did they see?
Oh, the paper shows some seriously impressive speedups, both for training the models and for decoding, especially as the text gets longer. At that 64,000 word mark, NSA was 9 times faster for training and almost 12 times faster for decoding compared to full attention.
Wow. That's kind of mind-blowing.
Right. I mean, think about decoding speed. That's crucial for anything real-time, like chatbots or instant translation.
Makes those interactions so much smoother, right? More natural.
Absolutely. But, it wasn't all smooth sailing for the researchers. Building something this groundbreaking, there were definitely bumps in the road.
Oh, I bet. What kind of challenges did they face?
Well, at first they tried adapting some existing sparse attention methods for training, see if they could tweak them to work. But they hit a wall.
What happened?
One approach they tried was clustering similar pieces of information together. Sounded good in theory, but it turned out to be super computationally expensive. And it just didn't play nice with this technique called mixture of experts.
Mixture of what now?
Mixture of experts. It's a way to, spread the workload across multiple processors. But this clustering thing they tried, it just clashed with that.
So it's like having a well-organized filing system, but all the files are scattered across different buildings.
Yeah, pretty much. And they also tried various block-wise selection methods, but some added extra calculations, slowing things down. Others weren't consistent enough in picking the right blocks, just didn't quite work out.
So lots of trial and error, lots of dead ends, but they finally found a way to make it work. And the results, well, they speak for themselves.
Yeah, it's really impressive how they went beyond just tweaking existing stuff. They completely rethought the whole process of training with sparse attention.
That's what makes it so groundbreaking, right?
Absolutely. Instead of just trying to make the model use information efficiently, they built that sparsity into the learning process itself.
Like teaching a kid a second language when they're young, it just becomes second nature.
Exactly. And that's what led to those clever design choices we talked about, the token compression, token selection, and that sliding window, all working together in sync with both how the AI learns and how the hardware actually operates.
Like a well-oiled machine. And that focus on practical application, that's what sets this research apart.
It's not just a theoretical model, it's built to work in the real world. And by making NSA more accessible to other researchers and developers, they've basically kicked off a whole wave of new possibilities.
So what's next? Where do we go from here? It's like we've been given this amazing new tool, and now the fun begins, right? Like, what can we actually build with it?
I honestly think we're just at the beginning. This kind of efficiency boost could open up whole new areas for AI, stuff that was just impossible before.
Yeah, like what? Give me some examples.
Okay, imagine AI tools that can analyze huge data sets in real time, or personalized education systems that actually adapt to how each student learns best.
Or AI assistants that actually get us, like truly understand our needs and respond in a way that feels, human.
Exactly. And it's not limited to just language anymore. This paper focused on text, but the ideas behind NSA, they could apply to other types of data too.
Wait, really? Like what else?
Well, think about applying sparse attention to images, or music, even scientific data.
Whoa, hold on. That could be huge, like breakthroughs in medical imaging, drug discovery, climate modeling, all that stuff.
Exactly. If we can make AI models more efficient across the board, it could seriously speed up the pace of, well, everything.
It's like we've stumbled onto a whole new way of thinking about AI, one that's both powerful and efficient.
And one that's like grounded in reality. The researchers didn't just come up with some abstract theory, they built a system that works with the way computers actually function.
That's so important. They didn't just stay in the ivory tower, they actually thought about how to make this stuff usable.
And by making NSA accessible to other researchers and developers, they've basically like lit a fire under the whole field. Who knows what amazing applications we'll see in the next few years.
It's like we've planted a seed and now we get to watch it grow into something incredible.
This has been a wild ride. Thanks for joining me on this deep dive into, efficient AI. And for anyone who wants to really get into the nitty-gritty, all the technical details, definitely check out the full paper. You can find it online using the ArcSieve ID 2502.11089V1.
And until next time, keep exploring.